All right, hello everybody. This is your week 1, day 2 lecture video for Math 32, Plane Geometry. We will be covering two sections, sections 2.2 and 2.3 as indicated here with this title slide. So we're going to dive further into truth tables and applications, and then in 2.3, we're going to introduce the conditional statement and also the biconditional. That's basically the related statements. Or actually, the conditional statement will have lots of different flavors, and then the biconditional is its own separate type of statement. And we're going to end today's lecture video with an outlining of that particular connective. And here we go. Let's go ahead and recall from last time one component truth table. Now that was the negation of P, and here it is all the way filled out. There's no place on your current lecture notes for you to rewrite this or anything. I just wanted to have you revisit this in your mind, or you can go back to your day 1 lecture notes in order to get a visual of this on your previous page. Now, please recall that I mentioned that since there was only one component, there would be 2 rows, one for the truth statement, or sorry, truth value for the component P, and then another row for the false possibility, right? There's only 2 possible truth values associated with one component, okay? Now, if you have 2 components, P and Q, like we had for our conjunction and disjunction tables that we introduced in the previous lecture video, please note that we have 4 different possible truth value combinations for the 2 components. Now, what does it look like when you have 3 components, right? So let's go ahead and entertain just with the initial columns, how they have to be initialized, not to reuse a word that I just, not the best sentence there. So what you may be wondering is, okay, if I have 3 components, generically call them P, Q, and R in a compound statement, that's what's going to be in this ... here, that we don't care what this is just yet. What we want to introduce is simply the standard way that you fill out these first 3 columns, okay? Now, since there are 3 components, you need to have 2 to the 3rd power number of possibilities here. So notice in this blank truth table that you have on your lecture notes, this is the very first thing on your accompanying lecture notes that I hope you've already printed out, and if you haven't already printed them out, go ahead and press pause and do that for yourself. How do you fill out those first 3 columns for P, Q, and R in such a way that you know that it's going to be the same initialization for every single other person that works on this or similar truth tables with 3 components, and that your answers will match mine and that they'll match the back of the book? So everybody's starting from the same position. Well, that first column, whatever the letter is associated with that, it's going to be the first letter in the alphabet among the 3 that are in the compound statement. In this case, it's P. The first column is going to be all T's on top, all F's down below. So T, 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 F, 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 if you're reading it from top to bottom, okay? Big chunk of T's on top, big chunk of F's down below is one way that I like to think about it. Now, for Q, the next column, it's got to be T, T, F, F, T, T, F, F. And you probably can surmise from context clues how R is going to go down as its truth value combination. It's going to alternate TF, 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 TF. Why do we do it this way? Well, we have to have a systematic way to initialize our truth table such that we're all starting from the same position, right? We all need to start from the same place, come from the same foundation, and then we do the work in this subsequent column of figuring out what the ultimate final answer combination of truth values is for the compound statement in question, which is what would be in this ... area. Okay, we're just going to leave that blank. Well, actually, hold on. Now that I'm looking at my lecture notes, I actually have a specific example that we're going to do here. So go ahead and with the specific example, you've already, I'm sure, filled out your P, Q, and R because it's the same no matter what the compound statement is right here. So let's go ahead and construct a truth table for this very first example, which is what you see in the first table, the first thing on the front page of your lecture notes in question. So basically this is what you're looking at right now, right? And you, oh, excuse me, let me go back, sorry. Giving away the process here before we're ready. Just make sure at this point that you have your T's and F's initialized for P, Q, and R in exactly this following way. And again, it's because we all need to be on the same page to initialize this work so that when we go through the process of figuring out the ultimate final answer combination of truth values, that we all have the same combination of truth values from top to bottom. Okay? Cool. So this right here, this compound statement that we're going to try to construct the truth table for, it's got, you may notice, a few different kinds of connectives and some grouping symbols going on here. So we can think of this, the process of going through and finding the combination of truth values for this entire compound statement in a order of operations type of way. There's going to be a first step and a second step and a third step, right? Until we find the outermost connective, which in this case is going to be this disjunction right here, okay? We're going to do what we do in trying to simplify expressions using order of operations. We're going to work with the innermost grouping, okay? And figure out the operations in the results of the operations inside, and then we're going to work our way out until we find the outermost operation, which in this case, like I said, is going to be this disjunction between these two groupings. Okay, so here we go. So you may be wondering, well, should I start with this grouping here or this grouping here? It actually doesn't matter so much, just so long if you want a rule of thumb, you always go with the left one. Okay, so by that I mean figure out the truth combinations for your R and go straight to the negation of Q. It would be too cumbersome, in my opinion, to underneath Q write true, true, false, false, true, true, false, false, and then underneath the negation write that, you know, the false, false, true, true that you see here. Rather than that, underneath the negation of Q, see how it's like underneath the middle, the midpoint between the space provided by the negation and the Q component? Just go ahead and write straight away what the negation is. And you know how I found this negation? I looked at this Q column and I said, oh, Q is true, true, false, false, true, true, false, false. Great. Underneath this negation of Q, which I need to figure out first before I do this conjunction between R and negation Q, I'm going to write just the negation of Q. Okay? Now, if you're real, you know, ambitious, you might be wanting to, instead of putting these initial T's and F's down, you may be like, oh, well, I can just look at these columns and figure out what the conjunction will be, and I'll just write this right here without writing these T's and F's. I mean, do you, boo, but I don't think that's a good idea. I think it's much better to write these T's and F's down and then focus on the relationship between them in regard to this connective, which again, the rule is for the conjunction, the and, right, connective, you have to have both true to be true, right? So just take this first space, for instance, and just focus on this T and this F. If you can join a true with a false, what is going to be the truth value of that conjunction? Well, it's going to be false, right? Okay, because you have to have both true to be true for a conjunction. So when will it be true? Here, right? Because these are both trues. And right here. Otherwise, all of these other rows here are going to have falses, right? See how there's a T here and a T there, but then every other case it's false. That's because we're dealing with a conjunction within these parentheses. Okay, so now this column right here that I'm hovering over with my cursor represents the truth value of this parenthetical statement. Therefore, the truth value combination of R conjoined with the negation of Q is from top to bottom, false, false, true, false, 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 true, false. You guys feel me on that? Okay, so if we feel good about that, let's go ahead and take this column right here, and then what do we need to do with this truth value combination? Well, we need to negate it, and we're going to do that directly underneath this negation symbol. So take this column, and every time you see a false, put a true. Every time you see a true, put a false. Right there, like that. Okay, so now this column is the truth value combination that represents this entire bracketed component. Okay, so the entire left-hand side of this disjunction, which is going to be our very last connective that we're going to evaluate, is known here. This is the truth value combination of this entire bracketed piece. Now just put a pin in that for now and move on over to this other parenthetical piece right here, and we're going to disjoin the negation of P with Q. So first things first, put the negation of P and Q down underneath those, headers right there, okay? So the negation of P, again, just look at P and notice that it's all trues on top and falses on the bottom, so the negation of it is going to be falses on top, trues on the bottom, right? And then for Q, just simply copy and paste it in your mind, right? Q is true, true, false, false, true, true, false, false. Cool. So row by row, consider what the truth value is according to the disjunction rule. The disjunction is associated with the connective word or, if we're doing it in English, right? And you only need one true to be true. So this one will be true, true, false, false, true, 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 right? There you go. Oh, whoops, I'm getting ahead of myself there. Okay, so now this column represents the truth value of this entire parenthetical piece here. Everything between these parentheses, its truth value is this guy. Now this truth value and this truth value combination here need to be disjoined in order to finish figuring out the truth value combination for the entire compound statement, right? This disjunction is the last connective, and it's going to be between these two columns that I've boxed up in green. I highly recommend that when you're going through really complex, compound statements with a lot of steps, that you maybe lightly or using different colors, that you highlight which columns you're trying to, in this case, disjoin to figure out the final answer truth value combination. So again, it's a disjunction. You only need one true to be true. The first value is going to be true disjoined with true. That's a true, right? And then true to true is true. And then go all the way down, and you should get the following values. The only time it's false is going to be in this third row, right, where both of the values being considered are both false. Otherwise, it's true. So this that I have boxed up in red, that's your final answer. And when you go through and you practice this in your homework, this column is going to be the only piece of information that you have to check your work, okay? So it's not, the back of the book is not going to give you all of this other information. It's just going to give you that. So if you have questions about what you're working on, if you're doing exercises and your answer does not match the back of the book and you initialized your initial component columns the right way, and so there must have been an error somewhere throughout here, that can be a good thing to ask about in the class period, and I'd be happy to demonstrate homework problems that anyone might be stuck on during the class period. Okay, cool. So let's go ahead and move on to De Morgan's law for statements. So De Morgan's law is just basically an equivalence for negating a disjunction or negating a conjunction. And so it turns out that when you negate a parenthetical disjunction, it becomes the conjunction of the individual negated components. So it's like you distribute through this tilde, so to speak, but you have to also change the connective from disjunction to conjunction. Similarly, if you negate a conjunction, it is equivalent to the disjunction of the individual negated components, okay? And we can transfer this. So this is the symbolic, right, version of the rule, but we can use it to rewrite English language statements. And it can get a little bit wild as far as the grammar is concerned. It can get a little bit clunky, but as long as you stick to the symbolic form of it, you can never go wrong. Okay, so here is one example that we're going to go through together. And it is, the original statement is as follows. It is not true that I swept and mopped the floor. So what we want to try and do with this statement right here is determine which 1, 2, 3, 4 statements, right, it most closely resembles. It is not true. Okay, so that's a negation symbol. It's only one mention of a negation. So it's probably going to be this one or this one, right? It's if you use the word not twice or some other form of that negation term, then you're looking at one of these guys, right? Not this and not that, not this or not that, right? Okay, but this was one instance of a negation term accompanied with the word and. And is the conjunction symbol. So I would say that this statement best is modeled symbolically here by where my cursor is hovering, okay? Right, so I'm going to match them up in red here, as you can see in this current slide. So that means it must be equivalent to, now let P be I swept, right? And Q can be I mopped, right? The floor. And so if you go ahead and take those pieces and just place them into these symbolic components with these negations and changing the and word to the or word, then you can rewrite it in the following way. It's equivalent to I did not sweep or I did not mop the floor. So again, there might be another way to write this in which the grammar or the flow of it is just a little bit better. But here is me just simply using the symbolic version that's equivalent to rewrite the statement. And that's going to be an exercise that you're going to endure in the upcoming homework assignment. So here's one example of using De Morgan's laws to rewrite statements. Okay, let's go ahead and introduce another type of statement, and it is a tautology. So you will now turn the page finally to the second page of your lecture notes, and we're going to define tautologies. There's a space for you to write this down. It's statements that are always true. So I would like you to write that definition down, and we're going to have an example in which we determine that the following truth table, which is set up right here, is indeed a tautology. So please, it's left blank for you because I want you to practice to fill out the initial truth table columns of Q and R. These are your statement components for this particular compound statement in the standard way. Q being before R in the alphabet, so it's the first column, is always TTFF for a two component, initial columns, and R being the second component, being TFTF. Always TTFF for the first column, for the first component, and then TFTF for the second component. Okay, now looking at the structure of this compound statement, you want to go for the innermost grouping, which in this case, you could look at it all stretched out here, or you could look at this right here and just say, okay, well, the innermost grouping is going to be this disjunction between Q and R. So that's where we're going to start. So I would put Q and R, just copy them down, okay, and then disjoin them. Remember, the disjunction rule is you only need one true to be true. So, or sorry, did I say disjunction? I am so sorry. This is a conjunction. Oh my God, terrible. If I said disjunction, I can't even remember if that's the word that I said out loud. This is a conjunction. Okay, equivalent to using the word and And the rule is you need both true to be true. So that's why only this first position is true and all the rest are false. I'm so sorry if I misspoke earlier, but let's just go ahead and move on if we're okay with that. The next most immediate connective after this is the negation. So let's go ahead and negate this conjunction, and it'll be false, true, true, true. And we're going to put that directly underneath this negation right here. Now this represents everything to the left of this conjunction here, still within the bracketed piece. So that means this negation of the parenthetical part is going to be now conjoined with the negation of Q. So go ahead, if you haven't already done so, write the negation of Q directly underneath here, okay? Which should be FFTT, in which you recognize that Q originally was TTFF, negating it FFTT. Okay, if it is helpful, go ahead and box up those two columns, because there's already a lot of T's and F's flying around. So, whatever organizational tool you use to focus on whichever columns are being, in this case, conjoined, go ahead and do something to focus on them, because you want to implement the rule, but only for these two columns in question, okay? So the conjunction of this negated parenthetical statement and the negation of Q is false, false, true, true. Okay, now this this column of trues and falses right here, this combination of truth values, represents the truth value of this entire bracketed piece. So now we must simply disjoin it with Q. Here's Q, right? Go ahead and put Q down, truth value combination, and maybe, circle them up so you can focus on being able to disjoin them, and that's going to be your final answer. What we find is the disjunction between Q and this entire bracketed piece represented by this column here. That is going to be our final answer. And so remember, the disjunction rule is you only need one true to be true. Well, in each row, according to the things that are boxed up in green, there's at least one true. So every single combination of possible truth values for the components here has an outcome of true. It's true all the way down. This is your final answer. So when your final answer of truth value combinations for a particular compound statement or any statement is all trues, that's what makes it a tautology. Okay? Cool. On the other hand, if you have a statement that is always false, you have what's called a self-contradiction. So there's a place on your lecture notes for you to write that definition down. Self-contradictions are always false. Here is our truth table. Go ahead and take a moment to initialize your P and Q statement component columns. P coming first in the alphabet gets true, true, false, false. Q coming next in the alphabet, being to the left of that, getting a truth value combination of true, false, true, false. Okay, now where do we start here? Innermost connective, right? So there's two winners, I would say, for the innermost connectives, the innermost operations. That would be this parenthetical part and then also this one. So which one should you do first? It doesn't matter. Creature of habit, though, I always go for the leftmost. So I'm going to start with this left side parenthetical piece in regard to this disjunction inside of the brackets, okay? Yeah, so I'm going to go for this first disjunction for the left parenthetical piece. So I wrote down P and Q components, and then I'm going to disjoin them. Remember, the disjunction rule is you only need one true to be true. So this will be the truth value combinations for the disjunction inside of this set of parentheses for P and Q. Okay, put a pin in that. Move on to the next parenthetical piece. Put down the negation of P and Q as such, okay? Focusing on these two columns here, go ahead and disjoin them. Remember, the disjunction rule is only one true to be true, so there's going to be only one false instance, and it's going to be in the second row. It's true, false, true, true. Okay, put a pin in this, I guess. Well, or rather, circle it. highlight it along with the disjunction in the previous parenthetical part, because that truth value combination represents this entire parenthetical piece. This column here under this other disjunction represents this other parenthetical piece. We need to highlight them both, disjoin them, right? And you'll notice that you get T's all the way down. Well, now if we stopped here, this would be a tautology, but wait, there's more. This column right here represents the truth value of this bracketed piece, and then to finish the compound statement, we need to negate it, and that's how we get F's all the way down, a self-contradiction by definition. So it didn't matter what truth value combinations we had for P and Q, and we investigated them all. That's the truth of that's the point of the truth table, is to investigate all truth value combinations for all of your statement components. That's the purpose of this organizational tool, okay? And in every instance, the statement was false. That makes it a self-contradiction, okay? Cool. Moving on. We are now in the next section. Good job, guys. So 2.2 section is in the bag. We're moving on to section 2.3, in which we are going to introduce a new connective, and that's going to be the conditional. Okay. So one thing that we want to keep in mind here as far as the overall theme of the conditional statement and this connective, this if-then connective, is that actions have consequences. There's always something that came before and then a subsequent result that is attributed to that initial action, okay? So I like to illustrate this with a very, I feel like, easy to understand and very relatable conditional statement that you're reading on your screen here, and you have it on your lecture notes, and it's the following. If you clean your room, then you can have dessert. I'm fairly certain that most people that are listening to this lecture video have had some sort of interaction with their parents in this regard, some kind of deal that was struck with the cleaning room and then getting some kind of reward afterwards. I don't know, specifying that it's dessert of some sort. Pick your favorite dessert, visualize it, that's what you get after you clean your room, right? Okay, so the initial thing in this particular conditional statement is the cleaning your room part. That's known as the antecedent, okay? Yeah, and conditional statements in general have two components. The antecedent is the thing that existed before. That's the you clean your room part, okay? The thing that comes after, or a thing that follows another, is the consequent. That's what I have highlighted in blue here. That's the you can have dessert component. So you first do the initial thing, the antecedent, and the consequent, therefore, should follow, okay? Now we're ready to turn the page of your lecture notes, and let's outline the truth value of the conditional. Now this is where it can get a little bit tricky as to being able to understand why the truth values for certain cases of the conditional are the way that they are. Some of them are easy to understand, I feel like, and then there's this one that's a little bit strange. So let's just go through them the way that I understand them, and we can have further discussion in class if it is warranted. So let's keep our example, and we're going to use that to fill out the truth value table that you see at the top of this third, I guess you would say, yeah, third page of your lecture notes, okay? So let's say that P is you clean your room statement component, and Q is you can have dessert, okay? And here is the truth table, the top that you have at the top of your lecture notes, and I've already initialized the T's and F's for P and Q statement components, okay? So what you would do in this case is you would go through each of the four cases individually in order to determine the appropriate truth value for the last column, the if P then Q, or P implies Q. There's lots of different ways, and we'll talk about those related statements in just a moment as far as being able to verbally describe this conditional statement here, symbolically depicted with the arrow going from P and pointing to Q. Okay, so case 1 is going to be both antecedent and consequent are true. That's associated with this first row, okay? Antecedent P is true, consequent is Q. So, and if we're going to maintain our original example here, in this scenario, you did indeed clean your room, and then you got to have dessert afterwards. That seems right, doesn't it? I mean, you did the thing, and then you got the thing that was promised you. So, hold inside of your heart that good feeling and put a T in this first row component of the third column, because that statement is true, okay? If it's true, if the antecedent is true and then the consequent is true for any conditional statement, so I'm talking about the symbolic, general, generic conditional statement, then the resulting conditional statement is true. But hopefully it was easy to illustrate why we think it would be true by the feeling we got with this specific example. I cleaned my room and then I got to have dessert afterwards. Both of those components were true. Okay, now take case 2. Antecedent is true, consequent is false. That's associated with the second row. So here is the next scenario. You cleaned your room, but you didn't get to have dessert afterwards. How do you feel about that? Not cool, right? That was not what we agreed upon. That seems like a betrayal, doesn't it? Don't you feel like you were wronged? Yes. Keep hold of that feeling and put a false in that position, right? That is not okay. I was promised dessert if I cleaned my room. I cleaned my room. I did not get dessert. That is just a travesty. Okay, so hopefully that feeling is going to help you remember that when the antecedent is true, but the consequent is false, the conditional statement is therefore false. Okay, so probably those first two cases were easy to, make sense of these resulting truth values. Hold on to your hats though, okay? Let's entertain case 3. Case 3 is a scenario in which the antecedent is false, but the consequent is true. Okay, so this is the scenario, if we're holding fast to our original example, you did not clean your room, got dessert anyway. Oof, how does that feel? Looks like you tricked the system, right? I like to call this scenario grandma's babysitting, okay? Because you can do whatever you want, and you're still going to get dessert out of her regardless of any of your behavior, right? You can do no wrong in her eyes. So, and if that is the case, then you might feel pretty good about this, unless, of course, you you feel guilty. But let's say that you don't feel guilty and you're just like, yeah, this is cool, this is right, I like this. Grandma is a cool lady, or grandpa or whoever is watching you, that lets you get away with everything. Yeah, and so hopefully we can hold fast to that feeling and be like, okay, that's true. So the overall consensus here with this particular case, and it bleeds into case 4, which we're going to talk about in a second, is that if the thing that was supposed to happen to initialize the consequence never happens, then the default is just to say that the result is true, because there was no first step that was taken, right? So it's like the process never really started. And so we have to have some kind of a default truth value associated with when this case occurs. And so it's basically like, if the antecedent is false, no matter what the consequent is, the outcome for the conditional is going to be true. Okay, so that's like the textbook version of why this case 3 has a true outcome for the conditional. Okay, now case 4 is similar, right? If the antecedent and the consequent are both false, I mean, if we're holding fast to our original example, this scenario would be like, I didn't clean my room and I didn't get dessert. That probably feels right and true, and like, okay, well, I would probably say that is true and fine and justice has been done because I didn't do the thing. Oh, hold on. Sorry. Let's go back. I didn't do the thing that I said I was going to do, so I shouldn't be getting the thing that, was promised to me. So hopefully putting a true in that case feels good. But again, going back to the textbook reasoning for, like the technical reasoning for why we would have this case 4 be ultimately true is because, again, the antecedent was false. Anytime the antecedent is false for a conditional statement, the resulting conditional's truth value is true. The only time a conditional statement is false, therefore, is going to be if you have a true antecedent and a false consequent. Every other time it's true. So that's the general rule, and hopefully that's going to be easy for us to understand. Let's go ahead and implement this rule as a part of a series of steps associated with constructing the truth table for this compound statement that involves conditionals and also a conjunction. Okay, so notice that we have two components, P and Q, so they need to be initialized in the standard way. And look for the innermost grouping for this compound statement, which will be this conditional on P and Q. Now here's P and Q, and as we just discussed, the only time the conditional is going to be false is right here where my cursor is hovering. So let's go ahead and put the T's and F's down here for the conditional. And then let's go ahead and move outward from this parenthetical piece and do this conjunction with P on the conditional, which is this column here. So there's P. If you want, you can always put some kind of highlighting markers around the columns that you're trying to focus on when you feel like there's just too many other T's and F's floating around. So you can just focus on the ones at hand. So here we're going to conjoin this conditional statement with P, and we will get the following. Because remember, you got to be both true to be true for a conjunction. So that'll be the following result. And then we're going to take this conjunction, which now represents the entire bracketed piece, and we're going to implement the conditional rule with P. So go ahead and put P's truth value combination down there. Maybe some intermediate boxing might be appropriate to focus on which columns are actually being implemented with the conditional right here. And then say, all right, if I am true to begin with and it's true as the output, then I'm going to be true, right? And then notice all the other antecedents here. They're all false. So automatically it's going to be true, true, true. True's all the way down. What is that? It's a tautology, y'all. Okay, so this particular compound statement involving some conditional connectives there ended up being a tautology because the final answer combination of truth values was all true all the way down. It's true no matter what. Okay, now let's go ahead and take a look at the equivalent forms of the conditional, and there are a lot. You may be noticing that the entire latter half of the page in your lecture notes are all a bunch of blanks, right? With bulleted points, if blank, then blank. So we're going to put P's and Q's in all of the corresponding blanks in particular areas depending on its equivalent format in the English language version of. This could be called P implies Q, if P then Q, right? That's actually the first one, if P then Q. That's like an English language way of representing. This is the most basic one. When you see this arrow, it's a conditional statement, and the most basic English language representative of that would be this if P then Q. But here are all the other equivalent forms. You don't even need the word then. That's the next bulleted one, if P comma Q. P only if Q. Okay, that one's pretty tricky because it's like, this time the if is in front of the Q, so you're just like, oh, is that right? Yes, only if, belongs in front of the consequent in this particular form. P implies Q. This is actually the one that I read off in my head when I see this symbology. I don't know why. This is P implies Q. It's like the arrow turns into the word implies for me, so I link this one up with this equivalent form all the time when I'm reading it. There's also not P or Q. Yup, a combination of a negation and a disjunction is equivalent to this conditional. Isn't that wild? There's also every P is a Q. This is lumping in a universal quantifier that we talked about in the first section. Q, comma, if P, little bit of a switcheroo on that one. Very confusing. Q provided P. Q is a necessary condition for P. So this is these last two are less used because they're just so wordy. This is if you're not into the whole brevity thing. All right, so yeah, make sure you got all your P's and Q's written down for that collection of equivalent forms of the conditional so you can familiarize yourself with them. Okay, we have a few more things to talk about with this conditional statement. Not much though. It'll be inverse, converse, inverse, and contrapositive. Now, if we were doing an in-person class, if I had my webcam on, I would show you some hand gestures. In fact, I'll cover this when we meet in class. It's basically a combination of thumbs up, thumbs down, and then switching the position of your hands from left to right. I'll show you all of that when we meet again in class. But in any event, let's just focus on the symbolic versions of these. So here is an original conditional statement: if P then Q, right? Or P implies Q, or any of those equivalent forms that we saw on the previous page. Its converse is going to be switching the consequent and the antecedent. So it's like P becomes P goes to the Q position, Q goes in the P position. You just kind of give them a switcheroo. Now, if you're talking inverse, that's going to be where you keep P and Q in their antecedent and consequent positions, but you negate them both. And if you negate and switch them, that's going to be the contrapositive, okay? So it's like the converse is the flip it, the reverse it, I guess I would say. Yeah, I'm trying to reference Missy Elliott here. Here's my Missy Elliott joke. Okay, the converse is you reverse it. The inverse is that you flip it. You flip both the P and the Q in the current positions. And the contrapositive is you flip it and reverse it. Is what Missy Elliott was talking about all along. Just kidding. That's not what that song was about all along. But anyway, make sure you fill in the blanks there with those symbolic forms. And let's go ahead and use a real English language sentence in order to a conditional statement using English. And we're going to let the symbolic forms help us write the converse, inverse, and contrapositive of this conditional statement. The conditional statement being, if it is a puppy, then it is cute. Okay, let P be, it is a puppy. Let Q be, it is cute. And how will the converse read? Well, remember, the converse is just switch the antecedent with the consequent. So it should read, if it is cute, then it is a puppy. Well, how would the inverse read? Well, negate both the antecedent and the consequent and their current positions, which would read as, if it is not a puppy, then it is not cute. Just negate those components in their positions. If you want to flip it and reverse it, that's the contrapositive, which reads as, if it is not cute, then it is not a puppy. Let me give you a second to write those things down, or if I'm moving too fast, at any time, you can always just pause the video so that you can catch up on your writing. You may notice that the feelings that you have about some of these, like the truth value associated with them, might be equivalent among some of these different versions of the conditional statement. So the original conditional statement, if it is a puppy, then it is cute. If you think that that is a true statement, right? I think it is. I've never seen an ugly puppy. Even those like hairless dogs, I still think they're super cute. Any dog, particularly in puppy form, is cute in my eyes. Then, think about the converse of that. Do you feel like the converse of that is necessarily true? If it is cute, then it is a puppy? Well, that would imply that only things that are cute are puppies. And it's like, no, there's other things in the world that are cute other than puppies, right? And then the inverse. If it's not a puppy, it's not cute. Well, what would that imply? That, if it's anything other than a puppy, it can't be cute at all. It's like, nope, I don't think that that's true. But go to the contrapositive, And again, this is all based on assuming that the original conditional statement is true, right? Then you could conclude that the converse and inverse in that case would not be true. Contrapositive, though, if it is not cute, it's not a puppy. Well, if the original conditional statement was true for you, then the contrapositive is also going to be true. And that gets me to my next point. Here is, and you have this on your lecture notes here already filled out, right? This is a 4-part truth table outlining the truth value combinations for an original conditional statement, right? This is just the conditional rule, right? If the only time it's false is when the antecedent's true and the consequence false, right? We know that. Now, if you're switching the positions of the antecedent and consequent, the false case moves down to this third case, right? Because we're going Q, then P in that order, okay? And it turns out that logically speaking, or technically speaking, the converse and the inverse are logically equivalent, like their truth value outcomes are exactly the same, and then the original conditional statement and its contrapositive are also logically equivalent to one another. So it's somehow in your notes, however you see fit, go ahead and make this conclusion here very clear. The conditional statement, a conditional statement and its contrapositive are logically equivalent, and also, disjoint from that, the converse of a conditional statement and the inverse of a conditional statement are logically equivalent to each other. But converses and conditionals are not, by definition, logically equivalent to each other. You can't just switch the position of the consequent and the antecedent willy-nilly for a true conditional statement and expect to get the same outcome. But for a biconditional, spoiler alert, you can. It goes the same backwards as forwards, okay? So here is an equivalent way of representing a biconditional statement, which we're just now introducing formally. Actually, it got technically introduced in day 1 lecture. With this symbol being like put in a chart and just saying, oh, it's a biconditional, and the phrasing was if and only if you see it in an English language setting. So it's equivalent to saying that I have the original conditional version of it, P, if P then Q, and it also has to be true that the converse is true as well. Okay, or they have to be both false. Okay, anyway, so hold on. Let me just put this in a truth table for you, and go ahead and initialize your P and Q columns, the T's and F's in the standard way. And which parenthetical part should you tackle first? It doesn't matter. I always go for the left one. So here is the conditional statement. Figured out its truth value. We already knew that, T, F, T, T, right? And then the converse will be T, T, F, T from top to bottom. Now do the conjunction for those, right? And that'll be what? Well, we want to focus on these conditional columns here and figure out the conjunction. All right, so basically you have to have both true to be true. So that'll be your final answer there. So it's the truth value combination for the biconditional in general is T, F, F, T. So consider the combination of T's and F's in the P and Q columns and then come up with the rule for it. The way that I think about it is, for the biconditional, either both components are true or both components are false. They have to match, okay, in order for the biconditional to be true. Otherwise, if the components mismatch their truth values, it's false, okay? Because with the switcheroo, you're going to have one of them being false and the other one being true, and that conjoined cannot be true, okay? Cool. So again, the biconditional rule is the components have to match in order to be true. And that's a wrap. Here are the suggested homework problems from the textbook. that I recommend that you tackle. And if you have any problems with them, please bring this up in our class period, and I'm happy to go over any of these problems or similar ones if you just want some more practice on a problem that you maybe even got correct, but you just want some more insight on. And then stay tuned and feel free to look ahead into 2.4. Section 2.4 is on arguments, which is going to be very exciting for us to be able to use truth tables and other mechanisms to determine if arguments are valid or invalid. Stay tuned for that. I look forward to seeing you very soon. Bye.